So today we are going to talk about limits at infinity again. Yes, we did do this at the very beginning of the year when we first talked about limits, but we are bringing that back up again today because I want to show you a new trick or tool that you can put in your calculus toolbox to help you find some limits. I know this unit overall is kind of a random hodgepodge of units, but it's kind of just where we took some random things that I couldn't find a good spot for, put them all together, and boom, here you go. So we did optimization on our last set of notes, and today we're talking about limits to infinity, or at infinity again. So real quick recap. What were the three ways we can find the limit of a function? I know it's been pretty good while since we've done this, but those three ways were, number one, we could do direct substitution. We could solve them algebraically. And then the third way, which we don't use very often, is that we could do them numerically using a table, numerically, I can spell, where you use a table and you get points that are infinitely closer to the number that you're looking at. It takes a while, not so fun, but you know, it is what it is. So looking at these two limits that we have right here, the limit as t approaches 4 of the square root of t plus 2, this one's a pretty basic direct substitution. I would just plug in the 4 and I would end up with the square root of 4 plus 2, which is just root 6. Now, what if this question had been written as the limit as t approaches 2 of, as t approaches negative 2 of square root of t plus 2. Okay, if that were the case, you have to think about, now you could do a direct substitution and some of us would be like, oh, but we get 0. It is actually not 0. If you look at the graph of the square root of t plus 2 is the square root of t shifted to the left 2 units, so 1, 2, so it looks like this, okay? Because this is not implying that it is a one-sided limit, it is a limit from both sides, there's only one side. Okay, there's only the right-hand side. If you wanted to find the limit as t approaches negative 2, you could only find the right-hand limit. You can't find this right here. So this would actually be does not exist unless we were to ask you for just the right-hand limit, and then it would be 0. I hope that makes sense. What about this next one? As t approaches negative 2 of t plus 2 over t squared minus 4. Well, we always want to try direct substitution first. That's usually our go-to. So we're going to say negative 2 plus 2 is 0. And then negative 2 squared is 4. Minus 4 is, oh no, we get the dreaded indeterminate. Remember, we can't keep this as equal to 0 over 0 because this the limit isn't actually 0 over 0. This is an indicator that there is another limit. We just have to try a different way to find it. Okay? And here we're going to have to do this algebraically. So we're going to rewrite this limit as t approaches negative 2, t plus 2 over, I'm going to factor the bottom and make that t minus 2 times t plus 2. And because that factors out really nicely, now I'm at limit t approaches negative 2 of actually just a 1 over t minus 2. From here, I can do a direct substitution, 1 over negative 2 minus 2, so I have a limit of negative 1/4. And that works out really well. Okay, we're not going to go over numerically because you're just plugging in numbers into a table, and that is boring. Okay, what about these? How did we solve these? Or have we done these? I don't know. Maybe we have, maybe we haven't. Okay, so we have a rational function with a radical in this first one, and it looks like we have a rational within a rational on the other one. I'm going to say that we're going to use the conjugate on this one. Now, typically in the past when you guys worked with conjugates back in Algebra 2, when you were rationalizing, we only worked with the conjugate of the bottom, but in this case, that's not really going to be helpful. So we're going to work with the conjugate of the numerator. So I'm going to multiply by the square root of 4 plus x plus 2 over root 4 plus x plus 2. So I've got the limit as x approaches 0 As I multiply the top, this just becomes 4 plus x. The whole point of the conjugate is that when you multiply the outsides and the insides, they cancel each other out once you add them all together, so I'm not even going to write that. And then minus 4 all over x times. Do not multiply all of this out. It's gross. There's no point. It usually is going to work itself out in the long run anyway, so just leave that as is. Okay? So then I've got the limit as x approaches 0. 4 plus x minus 4 reduces to just x over x square root 4 plus x plus 2. Oh, remember how I told you that this is going to just cancel out in the end and be pretty on its own? Yeah, found it. So limit x approaches 0 of 1 over square root 4 plus x plus 2. From here, I can plug in 0 directly into this. Oh, we were supposed to try that at the beginning, and I forgot. Let's pretend that we did. You would have ended up with 0 over 0. Oh no, 0 over 0. Okay, and then we just multiply back down to. Okay, sorry. Back to where we are. So now I'm going to plug in the 0, and I get 1 over the square root of 4 plus 0, which is just 1 over 2 plus 2, so 1, 4. Oh man, that's I think the first time that's happened to me today. That's actually kind of impressive. So 1/4 is the limit here. Okay. Over on this one, we have a rational with an irrational. Maybe it's easier if you look at it. X approaches 0 as 1 over x plus 1 minus 1 over x. Again, if I were to use a direct substitution, 1 over 1 is just 1 minus 1, so 0 over 0. Boo, destroy the evidence. We don't like that. This is an indicator that we must try something else. Okay? That something else in this case is to get common denominators. Okay, so you're going to have the limit as x approaches 0, 1 over x plus 1 minus x plus 1 over x plus 1 all over x. So limit x approaches 0. See if we can combine the top here. 1 minus 1 is just 0, so then minus it. So I have negative x over x plus 1 all over x. And then I'm just going to go ahead and put that denominator in another fraction there, so that way we can tell that I have a fraction within a fraction, which when we have fractions within fractions, we take the bottom and multiply. We flip the bottom and we multiply. My bad. X approaches 0, so negative x over x plus 1 times 1 over x. The x's will cancel out, so then you're not left with negative 1 over x plus 1. Now you can plug in your 0, and you're left with a limit of negative 1. Okay? So then let's keep going here. We kind of already reviewed this. Do you remember what indeterminate means? Well, hopefully. We just had 2 examples, actually 3 examples where we had an indeterminate situation. So that's where you have a 0 over 0. Okay? What does that mean? It means that you have a limit. We just can't tell what it is. We literally cannot determine it from the information at hand the way it is presented to us. So we have to kind of sort of, modify it in a way that we can actually work with it. Okay? So, let's see. So what about if we have infinity over infinity? Have we done these before? Yes, we have. We've used our in behavior asymptotes. Okay, does anyone remember the shortcut? There's actually 2 different types of shortcuts. Okay, we have bigger on bottom, which means if the degree of the bottom is bigger, then your in behavior asymptote is 0. Okay, if you have the bottom is equal to the top, the degree of the bottom is equal to the top, it is your leading coefficients. Okay, if it's bigger on top, then it is unbounded, and your limit is actually positive or negative infinity depending on which direction you're going. Another way to think about this is to say that this is bottom heavy, balanced, or top heavy. Just another way of looking at it. Depends on how you think of it. Either way is perfectly fine. Okay, moving right along here. Okay, so knowing those things, find each limit using your end behavior asymptotes. So this one looks pretty bottom heavy to me because the degree on the bottom is bigger. So my limit is 0. Okay, this one looks pretty balanced. So I'm going to look at my leading coefficients, which is going to be just the 2 over 3. So my limit is 2/3. And then as I look at part C, this one is looking, let's see, I'm approaching positive infinity, and this one is top heavy, so it's unbounded, but it's going to positive. So my end behavior asymptote would be like the line y equals x here, roughly. So then it's going to be positive infinity, which technically means my limit does not exist because it is unbounded. Okay, you can write infinity or does not exist. Either one of those is correct. Okay. Moving along. Oh, what about this? We have limit to infinity, but we have a rational function in the not a rational, a radical in the denominator. Oh, we do on both of these. Now, these are a little bit tricky here. So this is the square root of x squared. So if I were to look at the degree of this, the square root of x squared would essentially cancel out to just be x. So essentially this is balanced, okay? But I'm approaching positive infinity up top over what would be a positive, whatever this x value would end up being. So then this is going to also be 3 over root 2, because those are my leading coefficients. Okay. Now notice this question is very similar to this question, but instead of approaching positive infinity, now you're approaching negative infinity. Because you're approaching negative infinity, okay, that means this up here is going to be a negative. We already know that this is going to be a positive. So that means your limit is going to be negative 3 over root 2. Does that make sense? Hope so. Moving on. Some things that hopefully, I say green sheet. I change the color of that every year, so I don't know what color it is, but that chart that I gave you at the beginning of the year that told you to memorize all the things, hopefully we have these memorized by now. The limit as sine of x, limit as x approaches 0 of sine of x over x is 1, and the limit as x approaches 0 of 1 minus cosine x over x is 0. Okay, several ways to prove these. I hope we've already done that in the past. I'm going to assume that we did and just keep on a trucking here. You actually use this to help prove that, and then you use conjugate on that one. One stuff. The limit as sine of x approaches infinity. Sine of x is x approaches infinity. Well, sine of x looks like this. So as x approaches infinity, there is no limit. Now, it's kind of like a bounded. It goes between -1 and 1, but it never actually stops at a single solitary number or approaches it. So this one does not exist due to oscillating behavior. Okay. Ooh, what about the sine of x over x? Well, we've done that as x approaches 0, but have we done it as x approaches infinity? Maybe we have, maybe we haven't. But let's think about this. So sine of x over x, we know that it looks like this, divided by a function that gets infinitely large. So something that bounces between -1 and 1, divided by something that gets infinitely large, is going to look like this. So as x is approaching infinity, what's happening here? It's still oscillating technically slightly, but over the course of time, it gets closer and closer to 0. So the limit for that one is actually 0. Okay, so that's one thing you want to make sure you know. As x approaches 0, the limit of that is 1. As x approaches infinity, the limit of sine of x over x is 0. Be very, very careful with those. Sometimes we get those mixed up. Okay. 4 sine of x over x squared plus 1. Would you guys say that this is top heavy, bottom heavy, balanced, neither? I'm not sure. I would say that this is probably bottom heavy. Bottom heavy. This is again going to oscillate between 4 and -4. Okay, but this is going to get infinitely large. So something that stays between 4 and -4 versus something that's going to get infinitely large, okay, is overall eventually going to approach 0. Okay, so the limit for that is 0. Okay, limit as x approaches 0, e to the 2x minus 1. All right, well, let's try our standard direct substitution. E to the 0 is 1 minus 1, so 0 over e. Oh, okay, well, that didn't work. All right, so then let's see if we could maybe let's see if we can factor the top. So e to the 2x is the same thing as e to the x times e to the x. So I'm going to think of this as a difference of squares. This is e to the x plus 1 times e to the x minus 1. Okay, if you were to multiply these two out, e to the x times e to the x, e to the 2x, negative e to the x, positive e to the x, those cancel out. 1 and negative 1 multiplied at 1. Sorry, multiplied at negative 1. Over e to the x minus 1. Oh, well, that was super helpful because now I'm at limit as x approaches 0 of just e to the x plus 1. So I plug in my 0 here and I get e to the 0, which is 1 plus 1. My limit is 2. Ah, piece of cake. Let's go for a challenge. Okay, found one. Well, we already know that we can factor the top. We did that on the last problem. Well, let's try our direct substitution. It's different on the bottom. No, that still didn't work. So limit x approaches 0, e to the x minus 1, e to the x plus 1. Oh, well, that doesn't really help us with anything because I can't. What do we do, guys? What shall we do? If only there was another way. Well, guess what? There is. This is one more tool that we can use for limits. We like to call L'Hopital. Okay? There are various ways to spell this. Okay? But we basically call it L'Hopital. So sometimes we abbreviate it as LHop for short, but it's L'Hopital's rule. Okay? So what L'Hopital discovered, okay, this is kind of a long process, like a lot of stuff here, but just hang on. Okay. Let f and g be functions that are differentiable on an open interval. Okay, so you have two functions that you can take the derivative. Okay. Okay, they're differentiable and they contain c. Okay, but they might not be differentiable at c. Okay, that's fair. Assuming that g prime of x is not equal to 0 for any value in AB. All right? Except possibly at c itself. Okay, so c is this. C is important. If the limit of f of x divided by g of x as x approaches c produces the indeterminate form of 0 over 0, okay, then the limit as x approaches c of f of x over g of x is the same thing as the limit as x approaches c of f prime of x over g prime of x. Okay? So if I can't take the limit as is, that means I can take the derivative of the top and the derivative of the bottom and then take the limit. Now notice, this is not quotient rule. Okay, you are separately taking the derivative of the top function and the separate derivative of the bottom function. That you are not considering this as all one function. You're picturing it as two separate functions. Okay, so provided that the limit on the right exists or is infinite. Okay, provided that the limit on this side exists or is infinite. This also applies if it's any of the other indeterminate forms that we have had so far. So infinity over infinity, negative infinity over infinity, infinity over negative infinity, or negative over negative infinity. Any of these indeterminate forms, L'Hopital's will work. Okay, so let's kind of go back for a second. So we had this question a minute ago. I say go back, it was just, I already had it on the next slide. We already plugged in 0 over 0 and we got the indeterminate form. Okay, so in order for you to use L'Hopital's, you have to prove that the limit of the top gives you 0 or infinity, and the limit of the bottom gives you the same. So we're going to take the limit as x approaches 0 of e to the 2x minus 1. And we know that that is 0. X approaches 0 of x is also 0. Because you are considering these as the top function as f and this as g, you're considering them separately. Now we recognize that we can apply L'Hopital's. Okay? Because I'm gonna get the indeterminate form 0 over 0 we don't like. This is just kind of a formatting thing that you have to make sure that you do in order for you to apply L'Hopital's. So now when I actually apply it, I'm going to say the limit as x approaches 0. I'm going to say e to the 2x minus 1. The derivative of that is 2 e to the 2x. Derivative of 1 is 0 over 1. And now I can plug in my 0 and I get 2. Yes, no, maybe. Let me go back real quick for a second. So let's say we this question. We were able to do this question using our algebraic methods, right? Let's say I didn't recognize that. Let's say I use L'Hopital's. So limit as x approaches 0 of e to the 2x minus 1 is 0. Limit x approaches 0 of e to the x minus 1 is also 0. So I can apply L'Hopital. Okay? So then I have the limit as x approaches 0 of 2 e to the 2x over e to the x. Okay? These things reduce. Okay? E to the 2x over e to the x. That's going to reduce x approaches 0 to 2 e to the x, right? You just cancel one of them out. Well, same basis, you subtract your exponents, 2x minus 1. Okay. And then you plug in a 0 and you still get 2. That's the same limit we had from before. Okay. Are we convinced? No? Okay. Let's do some more convincing. This is a good one. Limit of sine of x over x. Okay. Okay. Limit x approaches infinity of the sine. Oh wait, that's not infinity. That's an indeterminate. Nope, just kidding. I don't want to do that one. Pretend I did not do that. You saw nothing. You saw nothing. That's what I thought. Okay. Oh. Same problem there. Ooh, this one. This is a good one. Okay. All right. I'm good. We got this. Limit x approaches infinity. 2x squared plus 5 is infinity. Limit x approaches infinity. 3x squared plus 1 is infinity. Apply L'Hopital. Okay, so when you apply L'Hopital, you take the derivative of the top. The derivative of the top is going to be 4x. The derivative of the bottom is going to be 6x. Okay? Again, here, if I were to plug in infinity, oh no, I get infinity over infinity. Okay, well, you know what? That's okay. Watch this. Limit x approaches infinity of 4x equals infinity. Limit x approaches infinity of 6x equals infinity. Apply L'Hopital. And you get the limit as x approaches infinity of the derivative of 4x is 4, derivative of 6x is 6. Oh, the limit of 4 over 6 is 2/3. Now, let's be real, guys. This is not the type of question that I would actually tell you, like, oh, use L'Hopital's. It makes it so much easier. It doesn't. That actually takes so much more time than recognizing your end behavior rules, okay? But it's just to prove to you that there was another way to do this. We've done the end behavior rules. We can also apply L'Hopital's. Lots of different ways to solve limits, and this is just giving you an extra tool to put in your toolbox to use for later, for when problems really actually need L'Hopital's. Let's get to another example. Okay, indeterminate form of infinity over infinity. Oh, we kind of already talked about one. Again, try direct substitution. The limit as x approaches infinity of the natural log of x over x. So, natural log of infinity is infinity over infinity. Oh no, indeterminate. Destroy the evidence. We don't like that. X approaches infinity of the natural log of x is infinity. As x approaches infinity of x is infinity. Because I get infinity for top and bottom, I may apply L'Hopital's, and now I get limit as x approaches infinity of the derivative of natural log of x is 1 over x. The derivative of x is just 1. So if I plug in infinity into 1 over x, I end up with 1 over 0. I end up with 1 over infinity, which we know is 0. Yeah, maybe, maybe not. Hopefully making some sense. Okay, let's try another one. Again, these are those opportunities where I want you to pause the video and give it a try on your own. See if you can get an answer. If not, come back, watch it and see if it makes sense, and then try it on the next one. Okay? So, applying L'Hopital's rule more than once. Well, we kind of already done that, but you know what? Let's go ahead and just, for grins. So, negative infinity x squared. So, negative infinity squared is positive infinity over e to the negative x. So, e to the infinity. The negatives will cancel each other out. So still infinity. Boo. All right. X approaches negative infinity of x squared is infinity. Limit x approaches negative infinity e to the negative x is also infinity. So I apply L'Hopital's, and I get the limit as x approaches negative infinity. Derivative of the top is 2x over the derivative of the bottom is negative e to the negative x. So I plug in and do direct substitution yet again. So then I end up with 2 times negative infinity over negative, oh man, I get negative infinity. Again, I get another indeterminate. That means there is still a limit. I just have to go a little bit further. So I'm going to do this all over again. Limit. Whoa. Limit x approaches negative infinity of 2x is negative infinity. Limit x approaches, maybe, whoa, approaches, come back. Negative infinity of negative e to the negative x is also negative infinity. So I can apply L'Hopital, and I end up with the limit as x approaches negative infinity of 2 over, well, the derivative of negative e to the negative x is just e to the negative x. So now I can plug in negative infinity here. E to the negative of negative infinity, so e to the infinity is basically infinity. 2 divided by that is 0. So my limit is actually 0. So this was an example where I had to use L'Hopital's more than once. Every now and then that happens. Not a lot. It just could. So you want to be aware of that. Okay? So other forms of infinity, of indeterminate, we actually have 0 times infinity, 1 to the infinity. Wait, what? So here's 4 different limits, okay, that are all of the form 0 times infinity. But you're going to see that every single one of them actually has a different limit. So here, let me just do this. Lots of words there. So limit, I feel like y'all are freaking out because of all the stuff here. So let's do my normal little trick here that I like to do. There we go. You see nothing. Okay. So x times 1 over x. Okay. So the limit of this, if I take x, if I reduce that, I just end up with a 1, right? But technically, if I leave it as x times 1 over x, well, that's 0 times infinity. Ah, my limit is 1 here. Okay. What if I wrote that as x times 2 over x? Again, this is 0. This is a form of infinity. So, yeah, like it's 0 and infinity. Now my limit is 2. Let's look at another one. Here, okay, now I have infinity times 0. So infinity times 0, which you would think would be the exact, well, over here it was 1, now it's 2, well, now it's 0. What on earth? What about this one? Here I have infinity times 0. These look almost the same, but oh, they're swapped here, but it's still 0 times infinity, but yet now my limit is infinity. Okay, so just because it looks like it, you should be infinity, like 0 times infinity, you would think like, oh, maybe it's 0, maybe it's, I don't know. It's actually indeterminate. We have to figure out what that is using L'Hopital's. Okay, so yeah. So we're going to actually look at some of those examples. So I'm actually going to pause the video right here. I'm going to actually make a new video for the rest of these. For some reason, my space is telling me that I don't have enough room. So just, yeah, there's another video. Just keep watching. Okay, I think I got it fixed, so let's keep on going here. So indeterminate form of 0 times infinity. As we've already seen from the last slide, there are different answers to this, so just because we think we know what it is, we really don't, okay? So if I were to evaluate using direct substitution, so I plug in infinity, e to the negative infinity would be 0 times the square root of infinity, so infinity. So again, this is an indeterminate form, so destroy the evidence. Now the catch here is that in order for us to use L'Hopital's, our function must be written as a quotient. Okay, so right now I have the indeterminate form. I have that piece of it because in order for me to use L'Hopital's, my function must be, number 1, indeterminate, and number 2, in a form of a quotient, okay? So what we have to do is to rewrite this to where it is a quotient so that way we can use L'Hopital's. So I'm going to recognize here that e to the negative x, that is the same thing as limit as x approaches infinity as square root of x over e to the x. Now this is written as a quotient or a fraction essentially. So if I were to plug in my numbers again, now I have infinity up top over infinity, which is another form of indeterminate, but this is a kind of form that we are able to use L'Hopital's. But we still have to go back and, specify that we are allowed to. So the limit x approaches infinity of the square root of x equals infinity. X approaches infinity of e to the x equals infinity. Apply L'Hopital's. Now I can already hear some of you guys asking me, Miss Murphin, is this part required? Yes. You have to do this part. You are not allowed to go straight from this step here down to here where you have already applied L'Hopital's, okay? In order for you to use L'Hopital's, you have to specify that all of the properties have been met. And this is how we specify those properties. So if and when I grade a paper that doesn't have this stuff on there, it's going to be a little while yet, but if that's not on there, yeah, it's going to be a problem. You have to have that. It is absolutely 100% required, okay? So make sure that it's there. Okay, so now I can apply L'Hopital's, so then I can take the derivative of the top, so limit as x approaches infinity. Derivative of root x is going to be 1/2 x to the negative 1/2 over e to the x. Derivative of e to the x is just e to the x. I'm going to rewrite this, and so now this becomes the limit as x approaches infinity of 1/2 x to the 1/2 e to the x. Now everything's nice and tucked away in the denominator, which is even better because then I have 1/2 times infinity. Essentially this just becomes 0. Okay, so infinity times 0 or 0 times infinity, we had to rewrite it in form of a quotient so that way we could use L'Hopital's, but then once we got that, then we can just apply L'Hopital's and we're good to go. Let's look at another example. This is the indeterminate form 1 to infinity. Just like the other forms of indeterminate, I have no idea what this answer is, but I do know that it is a form of indeterminate. So this, when I plug this in, I already know it's going to be 1 to infinity. Okay? No bueno. However, we know when it's indeterminate, we can use L'Hopital's, but it's got to be written as a quotient. Ooh, this one is a little bit tricky, okay? This is very similar to what we did back in derivatives where we had to do logarithmic differentiation. I know it's been a little while, but it was something that we did. We're going to do the same, something similar here. So the whole point of a limit is to come up with a y value that your function is approaching as x approaches a specific x value, or in this case as x approaches infinity. So what we're going to do is I'm going to rewrite this entire thing as y is equal to the limit as x approaches infinity of 1 plus 1 over x to the x, because essentially that's what we're going for here. That's the whole idea, is we're trying to get this y value, okay? Well, that's all very well and good, I'm sure you're saying, but you're like, Murphin, that doesn't help us out at all. Well, the main problem that I have here is this guy right here, okay, this exponent. I need to somehow move the exponent to a place where it makes life a little bit easier. The only way I can bring that forward is to use my logarithmic property. So what I can do is I can actually take the natural log of both sides. So I can say the natural log, oops, almost short limit, the natural log of y is equal to the natural log of the limit as x approaches infinity of 1 plus 1 over x to the x. And you're thinking, okay, that's okay, just bear with me here for a second. So now I'm going to take natural log of y. I'm going to take, so I can take the natural log of the limit. So basically, I can actually like just boop, 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 put that in right there and make this the limit as x approaches infinity of the natural log, oops, I did it again, natural log of 1 plus 1 over x to the x. Now this is a little bit better, okay, because what I'm going to do, natural log of y is equal to the limit as x approaches infinity. Now that I have the natural log of 1 plus 1 over x to the x, I can use my log properties to bring this out front. So I've got x times the natural log of 1 plus 1 over x. Okay, so we got rid of the exponent. So we're closer, but yet we still have, if we did direct substitution, this would be infinity, natural log of 1 plus 1 over infinity, so this would turn into the natural log of 1, which is 0. I still have infinity times 0, which is still an indeterminate, but I can't use L'Hopital's yet because it's not written as a fraction. So what I have to do is something that I did earlier. Remember how we did with e to the negative x on this last question? I was able to bring it to the denominator because I had a negative exponent. Well, I can do the same thing here. It just doesn't look like it, okay? So x by itself is just x. But I could rewrite this as the limit as x approaches infinity. I'm going to leave the natural log of 1 plus 1 over x up top over 1 over x. Okay, I rewrote this guy into the form of 1 over x, because if you think about it, when I divide by 1 over x, that is the same thing as multiplying by the reciprocal, which is just x. But I wrote it in this format specifically so that way I would have a fraction. So let me take out some of that extra stuff, okay? So now I have it in the form that I can actually use L'Hopital's, because I can't use L'Hopital's unless I have a fraction. So now I'm going to take the limit as x approaches infinity of the top over x, and I get 0. Okay, the limit as x approaches infinity of 1 over x is also 0. I can apply L'Hopital. How nice. Okay, so I'm going to apply L'Hopital's. Now don't forget, all of this still is actually just equal to the natural log of y. We can't forget that. So the natural log of y, you only have to apply L'Hopital's though to this side. There's no limit on this side, so I'm not applying L'Hopital's. I'm just dragging this down with it. So the limit as x approaches infinity, the derivative of natural log is 1 over 1 plus 1 over x. Remember, 1 over the derivative of the inside, and then times the derivative of the inside. Derivative of 1 is 0, plus this is negative 1 over x squared. okay, all over the derivative of 1 over x, which we know is negative 1 over x squared because we just did that up here. Well, the nice thing is those two things will cancel each other out. So now I'm left with natural log of y is equal to the limit as x approaches infinity of 1 over 1 plus 1 over x. Okay, here I can plug in my infinity because then I have 1 over 1 plus 1 over infinity, which is 1 over 1 plus 0, which is just 1. We're close, but we are not done yet. Remember, that's all equal to the natural log of y. Okay, so the natural log of y is equal to 1. I'm going to bring all that over here. Natural log of y is 1. Well, if the natural log of something is 1, to get rid of the natural log, you take e to the natural log of y is equal to e to the 1. Those two cancel out. Y is equal to e. So this whole crazy thing at the very beginning, up to the very top, this limit is actually e. And this crazy thing right here, guys, boop, 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 is actually what we call the limit definition of the concept of e. Wow, that does not look like an e because my computer totally glitched there. Of e. Okay, so you're like, well, why do we care? You know what? That's fine. You don't have to care about that yet. That's something that we're going to talk about again in the future. But just know that the process that we had to use here was to write it out as a y equals, because that's what the point of a limit is. And then we used the property of logarithms, so we can bring the exponent to the front and then bring that to the denominator, so we can use L'Hopital's. And then boom, 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 there you go. You end up with a limit of e. Okay, I have one more problem like this. I'm not going to work all the way through it. I'm going to, like usual, put the filled in version on Canvas for you guys to look at later. But yes, there's going to be another one on your notes. Let's see if there's any more that yeah, so this one right here, I have it on Canvas, so just check that back a little bit later. Give it a try on your own though and see how it goes. This one is the indeterminate form of infinity minus infinity. Okay, well, we know it's an indeterminate, but yet again, in order for us to use L'Hopital's, it must be a quotient. Luckily, these two things are already very close to being in that form because they're already two separate fractions. I just have to get common denominators. So I'm going to say the limit as x approaches 1 from the positive. Yes, you need to keep that because it's very important. Remember, we're approaching natural log of x is 1. Like, yeah, it's important. Just go with that. So common denominator would be x minus 1 over natural log of x times x minus 1 minus natural log of x over natural log of x times x minus 1. So then I take the limit. My computer is apparently not wanting to continue with the videos today because it's glitching a lot. That's okay. X minus 1 minus natural log of x all over the natural log of x times x minus 1. Okay. We plug in our 1 to see if we can do direct substitution. 1 minus 1 minus natural log of 1 is 0 over natural log of 1 is 0 times 0, or 1 minus, indeterminate. Okay, that's okay. This is where we do L'Hopital's. So we're going to say the limit, maybe, might have to, x approaches 1, positive x minus 1 minus natural log of x equals 0. Okay, so then when I apply L'Hopital, I end up with, oh, actually, well, yeah, we're good. X approaches 1 from the positive. So the derivative of x is just 1. The derivative of 1 is 0. The derivative of natural log is 1 over x. Over, here I have to use the product rule. Okay, so I'm going to have 1 over x times x minus 1 plus natural log of x times, just 1. Okay. From here, can I do, let's do direct substitution. That's not looking good. 1 minus 1 over 1 times 0 plus natural log, 0. Oh, shoot, we get 0 over 0 again. All right, well, we know what that means. We know that means we need to apply L'Hopital's again, but maybe, let's see if we can clean this up some. Maybe I missed something here. 1 minus 1 over x over, I'm going to go ahead and multiply this out. So 1 over x times x is just 1 minus 1 over x plus natural log of x. If I do it this way, no, that still doesn't help me out. I still end up with 0 over 0. Okay, so I still need to apply L'Hopital's one more time. So, 1 minus 1 over x equals 0. So apply, so I'm going to have a limit, x approaches 1 from the right of, okay, so the 1 is going to go away now. So then minus, this is going to be positive 1 over x squared over, the 1 goes away, 1 over x squared plus 1 over x. Oh, this is maybe looking a little bit more promising, guys, because now I plug in a 1, I have 1 over 1 over 1 over 1 plus 1 over 1. Oh my gosh, I get 1/2. The limit is 1/2. Yay! All that hard work, and we got a number. That's excellent. Feels good, right? Oh, it should. If you're not, if you don't, you know what? Fine, whatever. Okay. Let's see what else we got here. The forms 0 over 0. Okay, so these other indeterminate have been, okay, all of these are indeterminate forms. There are some forms that are very similar that are considered determinate, okay? Infinity plus infinity is just infinity. That is determinate. Negative infinity minus infinity is a negative infinity. That is determinate. 0 to infinity is 0. 0 to negative infinity is infinity. What? There are ways to prove these two. We don't need to worry about that. I feel like that's going to make some of you cry. And it might make me shed a tear as well. So, you know what? We're just going to we're going to accept that as true for now and move on. If you would like to look into that, you are more than welcome to. And I know some of you will, and I applaud your efforts. And I think that's fantastic. I will happily hear your findings when I return. Okay, let's see what else we got here. Oh, hey, there we go. That's the end of our video. So, yeah, that was part 2 of indeterminate forms. I might try to smush this together into one video if I can. But thanks for watching. As always, if you have questions, Prof. Rob Bob, Khan Academy, and your ever so helpful textbook.